Hey, this is Steven from RC Engineering, and welcome back to my development series for RC models and other to then apply to full-size models. So we're going to take a little hiatus on, obviously our thrust stand is done, so that series is kind of also on a hiatus. One of the videos that I use with thrust stand is on my analysis video. Is I guess one of my analysis video, and that was a few weeks ago. But this video we're going to be looking inside of the Tiny Whoov craze and see what we could give back to the community using our design and engineering skills. So if you guys don't know, Tiny Whoov is basically, let me see here. So this is the original developer. Tiny Whoov is basically a hovercraft built out of a Inductrix frame or a Tiny Whoop frame. Well, not a frame, but using the electronics from a Tiny Whoop. So you see here we have the camera, the small 3-gram all-in-one camera. We have the 6mm by, what were they, 15 can or 12 can or whatever. I have a few down here. The small can motors with the 40mm props, the standard Tiny Whoop props. And then you see the board. Some of these are built with this board here is the Nano QX board, the Blade Nano QX. Also, sorry, I'm a little under the weather, so this video is not going to be too long, otherwise I'll lose my voice. So this is the original inventor of it from Badass Drones. The very first of its kind, as you see. Somebody might have developed it before then and then they figured it out, or not completely sure. But there are a few different ways of building these. These guys are super sweet. If you want to, let me see if we... Let me turn off. So here you could see sort of how it works. So basically, if you're not familiar with how a hovercraft works, let's actually show you guys while this video is playing here. If you guys are not familiar with how a hovercraft works, so here's the bottom. I'm going to kind of go over the engineering of a hovercraft. And basically what you have is you have something that sits flat on the ground. Generally these are without skirts. And we'll go over what a skirt is in a second. But basically what you could have is, a lot of times the first project you guys have with a hovercraft is a disc. Some people, they take a disc and they put, so they take a CD disc or a DVD disc and they put one of those caps from a water bottle. And they put a balloon on top onto the nipple of the water bottle. And they fill it full of air. And then when they let that, when they pop the top to let the air through, and then this is sitting on a table, it'll actually hover. And so basically what is happening is the air is pushing down, and at first you have a high velocity. The tighter something is, the higher velocity, but the lower the pressure. The bigger something is, the lower the velocity, the higher the pressure. So basically what happens is the air rushes in here, and when it changes from this area to this area, the pressure increases. And for right now, in this particular scenario, you could think of it as linear, but it basically relies on Bernoulli's equation, which is to take something along a streamline, which you see is one streamline here, and then be able to use that equation, which is also used in CFD. Maybe later on we'll use computational fluid dynamics to show this, but you could think of volume with velocity with respect to pressure. Let's say times area up here or whatever is equal to, so this is number volume, this is the first velocity, and then velocity, say volume 2 times. And then these are the second stage, which is, oh man, it's really hard to right with the mouse. So as this guy decreases, right, the pressure's got to increase. So as the velocity in the area as the velocity is higher and the area drops down, then that means that the pressure has to increase, and velocity is going to decrease, I guess you could say. That's kind of a bad analogy, but you get the idea. So they're linearly related between velocity, area, pressure. They're all linearly related. So as velocity decreases, as the area decreases, then the pressure is going to increase and the velocity is going to decrease. As the area decreases, the velocity is going to increase, pressure is going to decrease. So increase, velocity slows down, pressure increases, and as it decreases, velocity increases and pressure decreases. That's what happens. So as it goes down here, you have a pressure change, and now all of a sudden the air is very extremely pressurized, but it's very, very slow. So what you have is the air will actually escape. It'll lift up this guy and escape through the side because it's under very high pressure. So basically what happens is the the pressure will act on the bottom of this disc, and the pressure is higher underneath the disc than it is around the disc. So basically when you have a pressure differential between high and low, the pressure is going to move from high to low. So basically it's going to create a force where this plate's going to lift up until the pressure equalizes, and it does that because all the air rushes out from underneath the disc or your hovercraft or whatever. So basically, because this disc is now hovering over the ground very, very slightly, so it's just like an air hockey table when you play air hockey, that instead of the hockey puck blowing down, the table's blowing up, and the puck will sit on a pressure of air, a little cushion of air. So what you notice is that when you run out of, let's say you're at a resort or whatever, and your quarters run out, and then so first you were playing and it was really smooth, and then all of a sudden the quarter runs out, and then you can't really play anymore. You hit the puck and it just like goes like a few feet and then it stops. While before you could hit it and it would bounce to their side back to your side like twice or 3 times. So basically the only thing now, rolling the friction against the ground is now eliminated because it's not touching the ground. So now the only thing contributing to this guy is air resistance, right? So air resistance is the only thing slowing this thing down now, because it is no longer in contact with the floor. It's only in contact with the air above the floor, which is also wind resistance, or wind friction, I guess you could say. Fluid friction, which is air. In this case, air friction. So what that does is allows you to go very, very fast. Now, some of the hovercrafts will have a skirt. What the skirt allows it to do is, as you notice, this will only work on a flat surface. Now, if you took this guy and you had like a little bubble here, what this is going to do is this is going to drop your pressure because there's a bigger area right here. Well, in this case it's volume, right? But it basically, all your air is going to rush down here, and because you have a bigger volume to fill, your force going upwards is going to drop. So basically what happens is, if that was the case, next thing you know, your hovercraft is no longer hovering because you lost all your pressure, because you lost all your upwards force. So now you're basically hitting this, you have a collision there, and you have a collision at this high spot. Also, another thing is it's no longer escaping from just the edges around the diameter of the disc. It's escaping throughout this big crack right here. So if you only have a flat surface, it's only going to work if you only have a flat disc with a flat bottom, or any hovercraft with a flat bottom, it's only going to work on a flat surface, or a relatively flat surface. For example, at my house I have grout lines in the grout and the tile. Now that might be okay, but anything deeper than that, you're going to have problems. So what some of the hovercrafts have that go over things like, hovercrafts still work over sand, water, other land, pretty much snow, pretty much anything, right? But what they have to have is what's called a skirt. What the skirt does is it keeps the entire side, and generally these are like strips, right? These are like stripped pieces. See, they look kind of like that, right? And basically, you know, it looks like a skirt, like a girl's skirt, and the girl's skirt isn't, theoretically you have to think of it, isn't continuous. Imagine if you cut it into strips so that it would contour to something, right? So it's designed to contour to the ground. So even if you had a bump in the ground, it's still sealed. See, it still has full contact there, full contact there. So there's no, still the air is only escaping through the bottom here, and you're keeping all the pressure underneath. So you're not getting any sort of leakage out the side of your pressure escaping, because you want to keep that pressure underneath and have as little of it escape as possible. So a skirt allows you to go over variable terrain with ease, while flat will only allow you to go, flat bottom will only allow you to go over flat terrain. So that's how a hovercraft works. You're pushing air down through, and it escapes to the side. The pressure change from the small orifice to a big orifice will increase the pressure, and that pressure is force over area. The pressure is higher on the bottom or inside the hovercraft than it is outside, so it's going to lift the inside of the hovercraft up towards the place of low pressure until the pressure equalizes. Because you have that lift away from the floor, you no longer have rolling resistance or friction. So now only wind resistance is affecting your craft. So how do we do that in a Tiny Whoov? And then, so some of the Tiny Whoovs have no skirt, and some of them do. Obviously, the better ones are with no skirt, but it really with skirt. But it really depends on what you're trying to go on. What we're going to be trying to build first is one that works on tile and hardwood floor, which is 99.99% flat. So we're not too worried about that. Okay, so as you can see here, these ones do not have any skirts. These ones are wholly flat, and then this here is just a piece of tape, I think, wrapped around just to change up the color. As you see here, it's kind of got this D shape, and what you'll notice, if we could pull up the thing files, they don't have a thing file for it. Let's look up some other Tiny Whoovs. Let's look at that one. This one will be pretty good. So this is what, let's go into thing view. It's going to load it up so we can look around the file, and you see exactly what I'm talking about here. So here's where you would contact the ground, and here's where the pressure would be caught, the air would be caught. And basically what it does is it uses two of the Tiny Whoop motors, right, or Inductrix, or Furry BF36, or Ishin E010, or whatever you're using, to push air down through this orifice. And then this is not going to be a lot of pressure, but when it changes from this area to a bigger area, it's going to increase its pressure. So here we're giving it a lot of velocity, and then the velocity is turning it into pressure, right? And we have two of those. Then when we do that, it's going to pick up off the ground just slightly. It's going to find an equilibrium where it's just slightly above the ground, and then the air is going to escape from around this guy, which we want. So now that we have that, now we're hovering over the ground. Now we could maneuver. So what we have is we have a left and right motor. Now, the board built into the Inductrix slash Furry Bee slash Ishin slash Tiny Whoop, whatever, has differential control for for left and right. So when you go left on your stick, what it's actually going to do is the right motor is going to spin faster than the left motor, and that's going to cause you to turn right. And then if you turn left, so if you turn left, this motor spins up faster, and then so you have this one going this way, this one not moving much, so it's going to turn around this way, right? Let's look at it straight up and down. Do they have straight up and down? No. I mean, there's this one, yeah, so, but it's flipped. Anyways, so if you turn left, this one spins faster. If you turn right, this one spins faster. And there you go. Now this thing will go really, really quick because you have no resistance against the ground for friction. And since you're inside, you don't have any wind blowing up against you. You're not really going that fast. You don't really have anything slowing you down either. However, out of the box with this kind of programming, which we'll probably get into optimizing the programming for Tiny Whoovs, whenever you let go of the throttle, whenever you bring down the throttle to control how much air you're pushing down or going forward, it's basically going to suck back down into the floor because you're no longer putting any pressure into this bottom cavity, and then you're going to come to a complete stop. So you can use that as control, or what we're going to do later is we're going to mess with Betaflight to get it to fly way differently than an Inductrix or Tiny Whoop or whatever. Then you see they also add the camera, 3-gram camera, and then the board, which in this case is underneath. And then they have the HV battery. And so you see a few different designs. But maybe what I wanted to do was I wanted to integrate some CFD into this guy to really get what we're looking for. So there's a few ways of building it. This is Flight Test, and they have another idea for how they run a skirt. So they use this guy, which this guy is basically the it's a piece of Delrin, I believe. Yeah. Wait. Drift bumper. It's basically a piece of Delrin. Delrin's a very, very low friction surface, so it allows you to slide on everything easier. So even if you kill the throttle, you'll still slide for some distance, and then that will also act as a skirt, kind of increasing the how it grabs onto the ground. As you see, it's cut up there a little bit. So there are two ways of making Tiny Whoovs currently. There should be three. Another one is vacuum forming. Vacuum forming would be very, very optimal for this design. We'll go into that later. So number one is foam, and number two is 3D printing. So 3D printing, obviously way easier to get a design printed, but the problem is you have to worry about supports. Another one is doing kind of like this, where you go with a Flight Test way and use a Dollar Tree foam board and stack them up till you get kind of the situation you want, and then you could either put the camera up here or you could have it kind of cantilevered out, whatever you want to do. And now there's some, and the number one thing that we're going to be looking at is with the ducts and without the ducts. So I've watched a few videos, and I'll explain later, maybe the next video, why the ducts are needed. But basically the ducts increase the efficiency of the props. It has to do with the differential of pressure from high and low. And we're going to explain later, and there are some videos out there that show that these props, these ducts are worth their weight in thrust. So they're worth their weight to have an additional thrust for the same amount of power. So they're definitely worth their weight having it on there. So basically what they did is they cannibalized a frame. They cut a frame of an Inductrix, Furry Bee, Ishin apart to get what they wanted. So here's one with a skirt. and you see the skirt here, and then what the skirt allows, and then this one's been printed in multiple versions. Let me see. So as you see here with a skirt, you're able to go over multiple surfaces here. You could go over jumps, you could go over carpet, you could go over rugs, you could go over snow, you could go over whatever you want. This one's made out of milk jug, I believe. And there you can see the skirt is made out of just a piece of plastic. I think it was a plastic bag with wrapped around a rubber band. So here you can see another one here going over jumps, landings, etc. Very, very, very difficult to do with a regular, and then here you see all the bumps. So this, basically his whole series here is talking about the benefits of having a skirt on the craft itself. So this one I believe is his most updated one here. This one's pretty nice. So yeah, so we're gonna go into building one. I would like to try to vacuum. It would have been nice to still have Tech Shop to try vacuum forming one. That's definitely the best bang for your buck, because that shape is so optimized for vacuum forming. You could have it extremely light, just crazy light, lighter than even foam will get you. Anyways, so yeah, so we're gonna go over, maybe do some 3D printing, maybe do some foam, and definitely doing some modifications to optimize the beta flight for Tiny Whoov racing or having fun with your friends. So what type of frame is that? Is that a custom airplane style frame? Do we have on motor? Do we turn off motor stop and just have these motors spinning up all the time, so it's always kind of skirting around, thus having your minimum throttle high, so it's already spun up to the point where it's floating, and then you just add left and right? Or could we get it to where the throttle is not even attached to these guys anymore and just attached to the back? Or is throttle not even involved? You just arm it. When it's armed, it's enough to fly, and then you kind of give it the more like the farther to the left and the farther to the right you go, the more it will speed up, or some sort of different mixing. So those are some ideas, and so we're going to be looking into those. But yeah, I hope you enjoyed this video looking at a few of these different designs, and you can kind of see that they all kind of have a similar thing going on. This is another thing we have to avoid, is the warping of the material there at the bottom. Alright, and here's some other ones where they're directed. So I guess this way you have a force downwards, and so technically you have a forward thrust from that downward angle. It's one way to do it, to where you get downwards pressure as well as mass of air accelerating one direction, causing you to be pushed in the other direction. Anyways, we'll look into it. And we have a few different boards. I have a broken Nano QX. I have a Ferrari BF36 that I need to do. I have this V1 B-Brain, which eventually I'll get a V2, and so that guy's programmable. Put it on this guy to mess around, because it does have some problems with low voltage gyro freaking out. And here's the ship. Alright, so that's pretty much it for this video. I got work here in the morning, so I gotta hit the sack. Anyways, so this is just a intro to the Tiny Whoovs. I'm really excited to build one. I've been wanting to build one for a while, and I might even like it even better than Tiny Whooping, because my house that I live at is really optimized for this. We have flat spaces everywhere, and very little carpet, so it's just perfect for what we're trying to do. Alright, so this has been Steven from RC Engineering, and if you guys like this video, please subscribe for more videos like it, and I'll see you guys in my next video. If you like what I do, please check out my Patreon in the description for some cool rewards, and also stay tuned over there for some more videos for some more free exclusive content to Patreon that I'm working on, and I'll let you guys know when that is released when the time comes. Alright, thanks guys for watching, and I'll catch you guys later. Take it easy. Peace.